Bridges, they've always been feats of engineering, but smart bridges, that takes innovation to the next level with advanced technology and cutting-edge design. For today's video, I'm going to count down 15 of the most incredible smart bridges. Number 15. The Øresund Bridge. The Øresund Bridge is a bridge-tunnel hybrid that connects Denmark and Sweden, serving as a vital transportation link between the two countries. Stretching nearly 5 miles from the Swedish city of Malmö to the artificial island of Peberholm, the bridge transitions into the 2.5-mile Drogden Tunnel, leading to the Danish island of Amager near Copenhagen. Completed in 2000, the Øresund Bridge was designed to address long-standing inefficiencies in transportation and improve border mobility, but beyond its primary function as a road and rail connection, the bridge incorporates some advanced technologies that makes it one of the most intelligent infrastructure projects in the world. The structure carries a critical data cable that supports internet communications between Central Europe and Sweden, demonstrating its importance as both a physical and digital connection. At the core of the bridge's design is the integration of smart tech. Automated toll collection systems allow for smooth traffic flow. Real-time traffic monitoring systems using sensors and cameras continuously track vehicle movement and detect hazards. Weather monitoring is another essential feature, with advanced sensors that track wind speeds, temperatures, and even ice formation. And that data enables operators to issue timely alerts and implement safety protocols. The bridge also incorporates structural health monitoring systems to ensure the stability and long-term functionality. Those systems were specifically designed to address oscillations in the bridge cables, ensuring the structure can withstand any stressors while maintaining its capacity. The transition at the island serves multiple purposes. It allows ships to pass through the unobstructed Drogden Strait, maintains air traffic clearance for nearby Copenhagen Airport, and it minimizes environmental and visual impact on the area. The bridge's towers, standing 670 feet tall, support the weight of both road and rail traffic, while the underwater tunnel ensures uninterrupted navigation. Number 14. The Rion-Antirian Bridge. The Rion-Antirian Bridge, officially known as the Charleos Trikoupis Bridge, is connecting the town of Rio on the Peloponnese Peninsula to Antirio on mainland Greece. Spanning the Gulf of Corinth, this cable-stayed bridge stretches 1.8 miles and stands as a transportation link in western Greece. It was opened on August 12, 2004, just ahead of the Athens Summer Olympics. This bridge was designed to overcome a unique combination of environmental and geological challenges, including deep waters, loose seabed sediment, frequent seismic activity, and strong winds. The Gulf of Corinth itself presents a set of problems that few other bridge projects have had to address simultaneously. The water depth in the strait reaches up to 213 feet, with a seabed composed primarily of loose sediment. To stabilize the seabed, engineers drove 200 hollow steel pipes vertically into the ground beneath each pier. Now, that was an innovative solution that ensures that the piers remain stable, despite the loose substrate. High wind speeds, which frequently exceed 70 miles an hour in the strait, posed another design consideration. To counteract wind forces, the aerodynamic fairings were added to the bridge deck to reduce drag and stabilize the structure. These spiral scruton strakes were also installed on the cable stays to minimize vibrations caused by wind. Over 100 sensors are distributed across the bridge to track seismic activity, wind behavior, structural strain, and environmental changes. 3D accelerometers measure vibrations on deck, pylons, and cables, while strain gauges and load cells monitor the tension in the stay cables. Temperature sensors, too, monitor freezing conditions on the deck, ensuring traffic safety during cold weather. And additionally, 2 weather stations gather real-time data on wind speed, direction, temperature, and humidity, feeding this information into an integrated control system. Number 13. The Gateshead Millennium Bridge. The Gateshead Millennium Bridge spans the River Tyne, linking the Arts Quarter in Gateshead with Newcastle's quayside. Open to the public in 2001, it was designed by Wilkinson architects and structural specialists Gifford. This bridge serves pedestrians and cyclists while incorporating an innovative tilting mechanism to allow the river traffic to pass beneath it. The bridge was conceived to address the need for a dedicated pedestrian and cycle crossing over the river, but without disrupting existing infrastructure. It was required to maintain a minimum clearance of 15 feet above river level during high spring tides, ensuring full accessibility for disabled users with a slope no steeper than 1 in 20. These constraints shaped the design into its final form, a tilting bridge capable of providing clearance for vessels while preserving seamless pedestrian access. One of the cool features of the bridge is the tilting mechanism. It's powered by 6 hydraulic rams, 3 on each side. During operation, the supporting arch lowers while the pedestrian deck rises, forming a 40-degree angle and providing 82 feet of clearance for boats. The entire tilting motion takes about 4 minutes, with the bridge rotating at a speed of about 18 millimeters per second. Now, despite the speed of the movement, the hydraulic system is remarkably energy efficient, costing just a few pounds per opening. As the bridge rotates, any debris on the deck naturally rolls into traps located at either end. At night, the bridge transforms through an intelligent lighting system designed by Jonathan Spears & Associates. White lights illuminate the structure on weekdays, while colored displays brighten the weekends. Red and green LEDs are integrated into the system to signal bridge openings and closings, ensuring pedestrian and cyclist safety. Traditional drawbridges often involve complex moving parts, heavy counterweights, and extended downtime during their operation, but in contrast, the Gateshead Millennium Bridge tilting design simplifies the process by treating the entire structure as a single moving element. Number 12. The Hong Kong-Zhuhai-Macau Bridge. The Hong Kong-Zhuhai-Macau Bridge is the world's longest sea-crossing bridge, spanning 34 miles across the Pearl River Delta. It connects those three major cities, Hong Kong, Zhuhai, and Macau, and it opened in October of 2018. The bridge was designed to address growing regional transportation demands and enhance the economic connectivity in the region. The idea for the bridge emerged in the early 2000s as a solution to improve transportation efficiency. Before its construction, travelers and cargo had to rely on ferries or significantly longer land routes. The bridge reduces travel time between Hong Kong and Zhuhai from just 4 hours to 45 minutes, streamlining the economic and logistical operations there. The bridge section spans 14.2 miles, while the undersea tunnel stretches 4.2 miles between two artificial islands. These islands, known as the Blue Dolphin Island and the White Dolphin Island, were designed to support the tunnel structure and ensure minimal disruption. Sensors embedded throughout the structure monitor activity, weather patterns, and structural integrity, allowing for predictive maintenance and immediate response to hazards. The bridge also uses adaptive lighting systems to ensure your visibility in varying weather without causing any light pollution. The durability of the bridge ensures a 120-year lifespan, far exceeding most large-scale infrastructure projects. It significantly reduces travel time across the Pearl River Delta, improving regional economic integration by combining bridge and tunnel components. It's going to maintain uninterrupted shipping routes while accommodating large cargo vessels. The undersea tunnel and artificial islands were constructed with any minimal disruption to marine ecosystems, including any protected habitats for the endangered white dolphin species. Number 11. Jindo Bridge. Jindo Bridge, located in South Korea. It's a pair of twin cable-stayed bridges that connect Jindo Island to the southwestern tip of the Korean peninsula near Haenam. The original bridge, completed in 1984, was Korea's first cable-stayed bridge, while the second bridge, constructed in 2006, was built to accommodate increased traffic demands. These bridges are notable for their impressive physical structure, but also for their integration of cutting-edge smart technologies. The addition of a second bridge in 2006 was a response to the rising traffic volumes, ensuring smoother traffic flow while also providing structural redundancy. Together, the two bridges meet essential transportation needs. The integration of smart tech has revolutionized the role of the bridge from a simple transportation structure to a hub of technological advancement. In collaboration with the University of Illinois at Urbana-Champaign and the University of Tokyo, a network of 113 iMote2 wireless sensors with 669 sensing channels was installed. These sensors continuously monitor the bridge's structural health, detect any potential damage, and ensure the bridge's long-term durability. The dynamic load distribution sensors measure stress and load patterns across the bridge, while the wind and environmental sensors monitor factors such as wind speed and temperature. The cable tension monitoring system tracks changes in tension on the stay cables, helping to identify any potential weakness, while the energy harvesting system reduces reliance on external power sources. The implementation of smart tech on the Jindo Bridge addresses several key challenges for civil infrastructure. Continuous structural health monitoring significantly reduces the risk of sudden failure. Additionally, the data-driven approach generated by the monitoring system improves maintenance efficiency, ensuring its stability during high winds and adverse weather. Moreover, the smart systems improve traffic management by optimizing vehicle flow. Number 10. Queens Ferry Crossing. The Queens Ferry Crossing. It's a cable-stayed road bridge located in Scotland, connecting Edinburgh at South Queens Ferry to Fife at North Queens Ferry across the Firth of Forth. Spanning 1.7 miles, the bridge is a significant modern infrastructure project designed to ease traffic congestion while also addressing some specific environmental challenges. Completed in 2017, the Queens Ferry Crossing stands out not only for its size and design, but also for its use of advanced technology that make it one of the most sophisticated bridges in the world. The bridge was conceived as part of the fourth replacement crossing project to relieve traffic pressure on the aging Fourth Road Bridge, which had been in operation since 1964. The need for a new crossing was further emphasized by increased traffic volume. The Queens Ferry crossing was designed to address those issues and provide a reliable, uninterrupted route for traffic. Construction of the bridge began in 2011 and completed in 2017. The bridge, with its three 679-foot towers, held the title of the world's longest triple-tower cable-stayed bridge at the time of its opening. Its location, close to the iconic Forth Bridge, ensures that it performs part of a critical network linking central Scotland to the northern regions. But what truly sets it apart from traditional bridges is the integration of smart tech aimed at improving safety, reliability, and operational efficiency. Wind is a constant challenge for bridges in Scotland, and the Firth of Forth is known for its unpredictable and strong winds. The system they use ensures that traffic remains uninterrupted even in extreme weather, which would otherwise cause significant disruptions. The sensors play a critical role in preventing issues like ice accumulation, which did lead to the closure of the bridge for the first time in February of 2020, 30 months after its opening, due to ice falling from the towers onto the carriageway. The automated wind shielding, for instance, allows the bridge to remain operational in conditions that would have led to closures on older structures. The temperature sensors further ensure that the structure can withstand the freezing temperatures common in Scotland during the winter. Number 9. The Akashi Kaikyo Bridge. The Akashi Kaikyo Bridge in Japan spans the Akashi Strait. It connects Kobe on Honshu with Iwaya on Awaji Island. When it was completed in 1998, it had the longest suspension span at 6,532 feet, or 1,991 meters. The bridge stands out for its advanced design, technology, and resilience in an earthquake-prone region. It's part of the Honshu-Shikoku Bridge project, which links Honshu, Awaji, and Shikoku across the Seto Inland Sea. The bridge carries the Kobe-Awaji-Naruto Expressway and serves local and long-distance traffic. The 1995 Great Hanshin earthquake tested its seismic resistance before it was finished. More than 100 contractors worked on it. Engineers equipped the bridge with wind, seismic, and structural health sensors to keep track of stress, wind conditions, and seismic activity. These sensors allow immediate adjustments and help predict how the bridge behaves in severe situations. A dual-hinge stiffening girder system also lets it withstand wind speeds of up to 178 miles an hour, or about 286 kph, and earthquakes as strong as magnitude 8.5. This design spreads forces across the structure, reducing any strain, and tuned mass dampers further control any oscillations by countering resonance. Deep underwater caissons support the tower in an area with strong tidal currents. The Great Hanshin earthquake caused a slight shift in the towers, so builders adjusted the central span. That flexibility became a key design factor in keeping the bridge stable. Temperature shifts on this bridge can expand the bridge by up to 6.5 feet or 2 meters, and that adaptation helps it stay safe and functional in varying weather. And sensors also alert maintenance teams when problems arise, allowing quick action to address any issues. Number 8. The Banpo Bridge. The Banpo Bridge in Seoul, South Korea stands as a blend of function and spectacle, offering much more than just a means of transportation. Spanning the Han River, what sets it apart from other typical structures is the integration of innovative tech and art, most notably through the Moonlight Rainbow Foundation, which holds the Guinness World Record for the longest fountain bridge in the world. The bridge itself is a vital route for vehicular traffic, but it also serves as a major landmark and tourist attraction. With a length of 4,905 feet and a width of 82 feet, the bridge is designed to facilitate not only daily commuting, but also public events and entertainment. The Moonlight Rainbow Foundation, inaugurated in 2009, is a display that features 38 water pumps and 380 nozzles capable of releasing up 190 tons of water per minute. The fountain operates about 5 to 6 times daily from April to October, and it's designed to recycle water to ensure some eco-friendliness. The water is shot out over distances of up to 140 feet horizontally and 65 feet vertically, making the display both a visual and environmental feat. The Banpo Bridge's integration of aesthetics and function serve the challenge of transforming a transportation infrastructure into a cultural space. It serves as a prominent feature in the cityscape, attracting locals and tourists, and it enhances the social and cultural life of the community. Moving on to number 7, Blackfriars Railway Bridge. The Blackfriars Railway Bridge, located across the River Thames in London, is one of the most forward-thinking bridges in the world, not just for its design, but for its innovative use of solar power. It holds the title of the largest solar-powered bridge globally thanks to its roof, which is covered with 4,400 photovoltaic solar panels. The panels generate enough electricity to power up to 50% of the energy required by the station, reducing its carbon emissions by an estimated 500 tons annually. It was originally built in 1886. The bridge has been a key feature in London's transport system, serving as both a railway station and a bridge. In 2009, the bridge underwent a major overhaul. The wrought iron structure was dismantled and rebuilt with a new roof equipped with solar panels. The roof spans over 64,000 square feet. It's roughly the size of 23 tennis courts, and it's capable of producing up to 1 megawatt of electricity on a sunny day. The solar panel system was designed to meet the high energy demands of the railway station. With the ability to generate that much power per year, the system provides enough energy to make approximately 80,000 cups of tea each day. While that renewable energy not only powers the station, but also helps reduce reliance on traditional energy grids. The solar panels were installed in phases over 2 years, and they were carefully timed to avoid interference with the 2012 London Olympics, and given the location of the bridge, there were logistical challenges in transporting materials, but the project team overcame those. But the meticulous planning and execution of the solar installation reflect the importance of this project, which has become a symbol of London's commitment to sustainability. And of course, sustainable tea. Number 6. The Scale Lane Footbridge. The Scale Lane Footbridge, located in Hull in England, stands out as a prime example of how modern bridges can combine functionality with innovation. Officially opened on June 28, 2013, this pedestrian swing bridge spans the River Hull, connecting the city's Old Town to an industrial area and planned housing development. The bridge is shaped like an apostrophe when viewed from above and features a cantilever design that allows it to curve upwards to accommodate boats of varying size. Its pivot point is a massive 53-foot hub, which supports the 1,000-ton structure as it rotates. The bridge has a capacity of about 1,000 people per crossing, making it an impressive feat of design and an essential part of the local infrastructure. But what makes the bridge smart is how it integrates modern tech to make the bridge functional for pedestrians and cyclists while solving the problem of accessing the river without disrupting any traffic. The use of these sensors and automated systems help monitor and control the movement of the bridge, ensuring that it opens and closes only when necessary. The bridge has a low operational speed, which reduces risks and creates an added layer of safety. The Scale Lane Footbridge solves a problem by allowing pedestrians to stay on the bridge while it opens for boats, a solution that wasn't possible before. This feature is especially significant in areas where pedestrian traffic is heavy, and the inconvenience of closing a bridge can disrupt movement in urban areas. Number 5. Tillicum Crossing. Tillicum Crossing, located in Portland, Oregon, stands as an innovative bridge. It spans the Willamette River, and it was the first major bridge in the U.S. designed exclusively for public transit, cyclists, and pedestrians, excluding private cars and trucks. Opened in 2015, the bridge addresses several challenges while integrating technology and sustainable practices to create a unique infrastructure solution. With a length of 1,720 feet, it features a 780-foot-long main span, and this design features a 180-foot-tall pentagonal-shaped tower, which serves as the focal point of the bridge's distinctive aesthetic. One standout feature is the use of Freycinet multi-tube saddle technology, which allows for cables running from the deck through the towers and back down. This design not only ensures stability but contributes to a cleaner, more streamlined bridge profile. The bridge is equipped with advanced LED lighting that reacts to real-time river conditions, and the system changes color and intensity depending on the factors such as Willamette River's temperature, the depth, and speed. For example, the base color of the lights is determined by the water temperature, while secondary patterns are based on the river's depth and current speed. This not only creates a visually captivating effect, but it also serves as a representation of the river's state. In 2019, TriMet further enhanced the bridge's sustainability with the installation of 12 vertical-axis wind turbines. These turbines, mounted on light poles at either end of the bridge, generate renewable energy from the wind. Each turbine can produce up to 1,000 watts of power depending on the wind speed. The bridge's design contributes to a cleaner, greener city by reducing car traffic and providing more room for buses, cyclists, and pedestrians. The energy generated from the solar panels and wind turbines is used to power the lighting and other systems on the bridge, reducing reliance on traditional power sources. Number 4. Smart Bridge of Eindhoven. The Smart Bridge in Eindhoven shows how new materials and technologies can reshape traditional infrastructure. It's part of the Smart Circular Bridge project in the Netherlands and highlights the future role of biocomposite materials. Built in Almere near Eindhoven, it spans 150 feet or 46 meters. It's the first of 3 pedestrian and cyclist bridges made from a flax composite. This is a renewable material that replaces steel and aluminum. Flax grows quickly and is widely available. The bridge has 80 sensors that track strain, vibrations, temperature changes, and moisture, and this data streams into a real-time public dashboard, and it helps researchers analyze performance under varying loads and conditions. The system allows for early detection of possible issues. It tracks how wind and heavy use affect the bridge, showing how flax composites hold up over time. Flax fibers, bioresins, and polyurethane foam blocks form a light but stable deck, and workers use flax mats around foam blocks in a vacuum infusion process. Handrails use a robotic winding method that wraps flax filaments in a cross-linked pattern. Optical sensors in glass fibers measure the strain and acceleration, while others pick up subtle vibrations. Now, this approach provides a deeper understanding of how the bridge will behave. By using flax and bioresins, this smart bridge responds to rising demands for greener materials. The real-time monitoring system will boost safety by giving engineers insight into changing conditions. But beyond its function as a walkway and a bike path, it also serves as a test for larger biocomposite projects. Researchers hope to use these materials for walls, columns, and beams. And early results suggest bigger structures with longer spans and heavier loads may be possible. Its focus on sustainability, new materials, and real-time monitoring sets it apart. Instead of steel or concrete, the smart bridge uses a more eco-friendly approach that may guide future construction practices. Number 3. The I-35 West St. Anthony Falls Bridge. The I-35 West St. Anthony Falls Bridge crosses the Mississippi River in Minneapolis, Minnesota, carrying Interstate 35 West traffic. This 10-lane bridge opened in 2008 to replace the previous I-35 West Bridge, which collapsed in 2007. The Minnesota Department of Transportation pushed for quick planning and construction to restore a key highway. Despite the tight timeline, the bridge features advanced smart technology for safety, performance, and environmental care. Construction started in late 2007 and finished on September 18, 2008, 3 months early. The crews used high-strength concrete with pilings driven 100 feet or about 30 meters into the ground. They poured over 50,000 cubic yards of concrete for the deck and piers. The workers built around the clock in shifts with 2 sculptures on the bridge that use TX active concrete, which helps remove air pollutants. Over 300 sensors are embedded in the bridge to monitor temperature, strain, and stress in real time, and experts at the University of Minnesota analyze this data to track performance under different loads and weather, with anti-icing systems that detect slick conditions and sprays de-icing chemicals, limiting any ice buildup and cutting down on extra maintenance. Plus, energy-saving LED lights brighten the deck and the architectural elements. Real-time monitoring flags signs of wear or damage, allowing early fixes and reducing long-term costs. That concrete mix includes slag and fly ash to lower any carbon output and reduce water and chlorine penetration. TX active concrete sculptures convert harmful particles into less toxic substances and stay clean with minimal upkeep. Instead of relying on standard materials and methods, the bridge combines smart sensors, self-cleaning concrete, and an automated anti-icing system. This approach supports durability, safety, and responsible engineering. Number 2. Slauerhofbrug. Located in the city of Leeuwarden in the Netherlands, the Slauerhofbrug, also known as the Flying Drawbridge, stands as a prime example of modern bridge design. It's a fully automatic bascule bridge that utilizes an innovative tail bridge mechanism. Now, this bridge, named after the Dutch poet, not only serves as a functional crossing, but also represents a remarkable leap forward in the way bridges interact with both road and water traffic. Instead of rotating from 2 hinges, it raises using a single pylon, which lifts the roadbed vertically, akin to flying the roadway out of the way. This tail bridge design allows the road section to be completely separated and raised 10 times a day, typically for passing boats. The mechanism that powers this unique movement consists of 2 hydraulic cylinders located within the pylon, which quickly raise and lower the bridge. This allows the bridge to move faster and more efficiently compared to conventional drawbridges, which often take longer to open and close. With a 50-foot by 50-foot deck, the bridge can handle heavy vehicle and pedestrian traffic when closed, while its quick motion prevents any significant delay. This approach makes it an efficient and reliable system for busy waterways where frequent boat passage is required. This eliminates the need for manual operation and ensures that the traffic is impacted for only a brief period each time the bridge is raised. The The structure itself is built from iron and steel, and its distinctive yellow and blue colors reflect the flag, giving it both a functional and symbolic significance. The vibrant colors and modern design of the bridge also serve to enhance the city's visual landscape. The slower Hofbrug serves several key issues that are common in cities with busy waterways. First, it addresses the challenges of providing quick and efficient passages for both boats and vehicles, and traditional drawbridges can take much longer to open. This bridge, with a single pylon mechanism, allows for a faster, more streamlined process, making it an ideal solution for cities with frequent water traffic. Number 1. The Millau Viaduct. The Millau Viaduct, stretching across the Tarn Valley in southern France, is not just the tallest bridge in the world, but also one of the most advanced. Completed in December of 2004, this cable-stayed structure serves as a critical link on the A75 autoroute, connecting Paris to the Mediterranean coast. Before the Millau Viaduct was constructed, the town of Millau faced significant traffic congestion, particularly during the summer months. Vehicles traveling between Paris and the southern coast would bottleneck in the narrow valley roads, causing delays and straining local infrastructure. After an extensive design competition, a multi-span cable-stayed bridge was selected for its ability to span the valley with minimal disruption. Construction of the bridge began in December of 2001 and was completed in just 3 years, an impressive timeline considering the scale of the project. The pylons were built using sliding shuttering techniques, which allowed them to rise 13 feet every 3 days. The tallest pylon, Pier 2, reaches 803 feet above its base, supporting a road deck suspended over 890 feet above the Tarn River. Despite the project's scale, construction was completed on budget, on time, and without any fatalities. But what truly sets the viaduct apart is the integration of advanced tech for monitoring and maintaining the structure. Wind monitoring systems measure wind speeds in real time, enabling operators to assess its stability. Temperature sensors detect any fluctuations that might cause the steel and concrete components to expand or contract. And additionally, piezoelectric sensors embedded in the road surface track vehicle weight and speed, plus traffic density. These sensors are capable of identifying 14 different types of vehicles, allowing traffic patterns to be analyzed and managed effectively. The Millau Viaduct solves multiple challenges simultaneously. It eliminates chronic traffic congestion in Millau, reduces travel times along the A75, and minimizes environmental disruption in the valley. Its combination of smart systems, efficient construction techniques, and environmental sensitivity ensures that it will remain both a durable and adaptable structure. Unlike conventional bridges, this viaduct is not merely a passageway. It's a carefully designed system capable of responding to environmental and operational changes in real time. Thanks for watching, everybody. I'll see you next time. Thank you to our channel members.